There's one more method for estimating a Hausdorff dimension of a set. It involves a quantity called energy. So given a Radan measure mu and a positive number s, we define its s energy to be this double integral of the Riesz kernel x minus y to the minus s. The connection with Hausdorff measure goes as follows. So first, let's define the set M of A, which is equal to the set of all Radan measures of positive and finite measures supported in A. Then for any Borel set, the Hausdorff dimension of A is equal to the supremum of all values s for which there exists a measure in A of positive and finite measure who's of finite s energy. So the proof is not too bad, so we'll go through it rather quickly. So we first prove the forward inequality, that the dimension of A is at most this supremum. So it suffices to show that for any s strictly less than the dimension of A, I can find a measure mu of finite s-dimensional energy. So to do this, I pick a value t strictly between s and dimension of A. And since dimension of A is strictly bigger than t, that implies that A has positive t-dimensional Hausdorff measure. And so Frossman's lemma tells me that there is a t-Frossman measure mu supported in the set A. So now I estimate the s energy of this measure mu. So first of all, recall that the s energy is this double integral x minus y to the minus s d mu. So the first step that I do is I take this inner integral and rewrite it using this identity. Okay. So now, so this is the measure of the set of x's such that y minus x to the minus s is bigger than lambda. What I do is I rewrite that set by taking both sides of this inequality to the power minus 1 over s, and I get that this is the same thing as this set. But you'll notice here that this is just the set ball centered at y of radius lambda to the minus 1 over s, which means that because I'm taking the measure of a ball and mu is a t-Frossman measure, that means that I can estimate this, the measure of this ball using the inequality in the definition of Frossman measure. Before doing that, I split the integral from 0 to infinity into two integrals. So first from integral from 0 to 1, and in that case, I just bound the measure of this ball just by the measure of all of Rn. And then you'll notice that this is a finite integral because I'm integrating, so mu of Rn is a finite number. I'm integrating it from 0 to 1, and then I integrate it with respect to mu, which is a finite measure. Then the integral from 1 to infinity, I use the Frossman bound. The measure of this ball is at most the radius of the ball to the power t. So that's lambda to the minus t over s. And now because t is strictly bigger than s, this is lambda to a power that is strictly less than minus 1. So thus, this integral is just some finite number, and I integrate that with respect to mu, and that is less than infinity. So thus, I've exhibited a measure supported on A with finite s energy for any s less than dimension of A. So now we'll prove the opposite inequality, that the dimension of A is at least the supremum of this set. So let s be some number strictly less than supremum. If I can show that any such s is less than dimension of A, then I will be done. So by definition of this set, if s is less than the supremum, then that implies that there exists a measure mu of supported in A with finite energy. So this energy being finite, that's saying, in other words, that the integral of this function as a function of y is finite. So thus, by Chebyshev's inequality, that should mean that there is a subset of the support of mu where my function is bounded. So specifically, Chebyshev's inequality implies that there is a constant m and a subset e of positive measure such that for all y inside this set, my integral, this integrand, is bounded by the number m. So now, if I restrict my attention just to this ball centered at y of radius r, then notice that x minus y is going to be at most r, which means that x minus y to the minus s is going to be at least r to the minus s. And so this integral here is just at least r to the minus s times the measure of the support of the integral. And thus, if I multiply both sides by r to the s, I see that mu is a Frossman measure on this set. So in particular, or at least for balls centered on this set. So thus, if I look at the measure that is mu restricted to this set, this is an S Frossman measure. And that implies the dimension of A is at least this number S, and I'm done. So in the next video, we'll see how convenient S energies are by demonstrating how to use them to estimate the Hausdorff dimension of orthogonal projections of sets.